Today, we will be talking about cabling standards and how they apply in the manufacturing spaces. The idea behind this session is to give everyone an overview of these standards and also at the same time talk to you about Panduit connectivity solutions that apply in industrial spaces and manufacturing, in the real world, in other words. At some point in this presentation, we will also discuss Panduit connectivity, network infrastructures, and I'm happy to answer any questions as Jane just mentioned, so please post your questions as they come up. Thanks again for joining me. So we are dealing with several standards when it comes to connecting Ethernet networks in the factory systems. These standards are divided between common standards, which apply in industrial and commercial spaces, premises standards, which specifically discuss how we apply it in commercial, residential, and industrial, and components. And those standards basically are governed by a consortium that's called TIA in the Americas. It's also used and applied by European norms and international standards. But for the sake of this conversation today, we will only be discussing the TIA standards. So TIA 568 is a common standard that is used and was initially created to discuss how the network, the communication networks are deployed in general. That standards evolved over time and several additions were added to it. So the CO version defined the overall premises and how infrastructures are laid out. Version C1 and C2 addresses different things. So C1 addresses commercial and C2 addresses how twisted pair connectivity in the copper side is used. So when we start looking at the different sections of that standards, you need to be made aware of all the different segments of it and how it applies. TIA 1005 and 1005A, and specifically, is the portion of the premises standards that we will be discussing at great length today. And the reason for that is because a lot of what is inside 1005A apply to the world we operate in. I come from industrial manufacturing, and I have worked in those spaces all my life. And you will see that when you go into a factory, you are dealing with the real world. And the real world means you are encountering all kinds of hazards that you need to be made aware of. And therefore, all of your networks have to be deployed to withstand those hazards. So with this said, I'm going to point out that between 568 and 1005, there are some specific differences that we will address here today. For instance, in the 1005, there is a standard for connectivity connection points that we call the M12 type connectivity. Those are similar to RJ45, which you will use in the commercial space, and they're mentioned in 568 standard, but the M12D and X codes are different methods of connecting Ethernet in the factory. This was mentioned in 1005A, and this is an important differentiator between the two standards. So you need to use, for the most part, in factory systems, at the edge devices, those types of connectors, not the RJ45. Additionally, in the 1005A spec, you will see that there is additional increased number of connection per channel that extended the 568 from 4 connector per channel to 6 connector per channel. And that's a differentiator also that you need to be made aware of. There is a major change also we will address today and has to do with something we call MICE. And the MICE rating, and it stands for mechanical, ingress, climatic, and electromagnetic, is our focus today. So we will talk about 1005A MICE specifications and how it applies for some of what we do. So when we look at these standards, and if you open up the 568 or the 1005, you will notice that there are structuring for how a network can be and should be laid out in commercial and industrial. And what you see on the left-hand side at the top is basically what we call a star topology. In a star topology, we are looking at how a network is communicating from an edge device at the EO level, at the very lowest point in a communication network, which in the commercial space, it can be a computer, a laptop. In the industrial space, it could be a sensor. It could be any type of an edge connection that is basically taking data and pushing it up to the rest of the network. And you will see in the star topology that at the edge devices, connectivity there are many of those connection points. And as the data and the connectivity goes back to the center point in the star, you will see that there are congregation points, which we call distribution A or distribution B or distribution C. Those are places where we will apply switches and routers. So a lot of these edge devices communicate to a switch, and then a switch communicate to another switch, and so forth. So you will see in this architecture that there are different types of devices that we will apply at every point in this network. Now, you will see in the picture on the bottom left that as we apply the MICE specification to this network, you will see that there are some places where you need to apply a strict differences in what type of cables and connectors you need to use. I will walk you through it in this way. When you look at a mechanical element in this MICE specification, you are concerned with vibration, you are concerned with shocks, you are concerned with flexing. So the edge devices and factory systems are exposed to extreme conditions, and it is not always the case. So if you go to a robotic cell, for instance, there's a constant flexing that takes place at the mechanical device. So cabling that's connected between an edge sensor on the robotic arm to its base, that cable connection point is taking a lot of abuse over time. And that changes the environmental severity that needs to be applied in that instance. So when we look at the MICE for mechanical or any of the other elements, if it is at a state 1, that means it can be an office style environment. In an office, a cable is laid out and it never moves. So therefore, this is the lowest rating for this mechanical element. Similarly, when we look at other elements, you will see that the rating changes the same way. So let's look at what is MICE. MICE is a major element of the TIA spec. Like I said, 1005. There is a big section in the specification that talks to all of the different changes that affect the mechanical system, the ingress and other elements, and the consideration for a lot of these elements as we start implementing a system need to be looked at. So I'm going to take you through this table. In this table, this is a quick method to look at what it means on each and every one of those segments. So for instance, on the mechanical, we are concerned with shock, vibration, crush. Crushing a cable is a real hazard out in the factory. So a lot of these cables can be severed very quickly if they're not configured, if the jacket on these cables are not done the right way. Impact. A lot of these connection points take a lot of abuse from different external hazards. When you look at the I element, the ingress element, we are basically concerned with water and dust. And you could have different concentration of water and dust in a given environment. So it starts from absence of dust and water to presence to intermittent presence to immersion. So there are some connection point in tanks, for instance, where a connector has to be immersed in water. And if that's the case, you still need your communication to pass from the edge point to its intended target. But that's an extreme environment that you need to be made aware of. When you look at the chemical aspect, what we call climatic, but one way to look at it would be chemical or presence of chemicals. Again, it starts from absence to interim presence to constant presence. And also, it talks about its toxicity. There are a lot of chemicals that will attack the plastics and the TPE and all of the different jacketed material that exist on the connector and all the cable. So you need to be made aware of what type of protection does my connector have to withstand, say, a extreme chemical or a caustic environment that are being deployed in. And the last element in this table is the electromagnetics. Electromagnetics are elements in the environment where we have to worry about power systems. Every single power systems in a factory emit a lot of electromagnetics. How do you know? If you walk around with your telephone, your cell phone in a factory, you stand next to a power conduit and you try to make a phone call, most of the time you hear a lot of static. That static electricity is not just affecting your communication, it's also affecting all the wiring that's laid out in that area. So there is radiated RF signals that come out of these power systems that cannot be helped. And we need to be very cognizant of these RF signals and other emissions that come out of the power systems that affect the communications. You will find those issues around drives. You will find them around power cabinets. You find them in many places around the factory. So when you start looking at all of these elements, what we call the mice, you need to be made aware that the presence of an element or the absence of element are immediate concern. But then you have to worry about the extent of that presence and how it affects my system. So if it's at a 1, that means it has no effect and it's not an issue. As the level increases, it moves from 1, 2, and 3. So here's another quick way to look at it. So as environments change from no presence to extreme presence, it changes. And that's how we recognize in that specification, the 1005, how certain cable or connector is able to withstand that environment. So then, if you look at a factory system, you would think that all of these different areas are alike. In fact, they are not. Why it is important to look at a layout in a given factory system and decide where is my extreme environment? Where can I, or do I need to be careful what type of networks, cabling, and connectivity I need to apply? So when you start looking at these areas, you would start with, say, a control room. In a control room environment, this is a place that's as close as it gets to an office space. What do you expect to find in those control rooms? You will find desks and tables, and you'll find maybe a data center where it's similar to what you see in the enterprise space, but it is intended to communicate in the factory, so it's connected to other areas around the factory. That is an environment where it's as close as possible to an office. So therefore, any kind of cabling that you run in that space will be designated as M1, I1, C1, and E1. When you start looking at the rest of the work areas, you will recognize that in some instances you have similar environment to control room. And where do you find that? You find it as you look at the entire manufacturing space. There are places within the manufacturing space, say at the ceiling level, where you're running generally all of the main communication. This is a space that is not seeing a lot of environmental conditions. As you go down to the floor level of a given work area, you will start seeing more restrictions. So at the ceiling level, you could still be at a control room rated environment. The only thing we need to worry about in that space is some emitted radiation. So there could be some power systems running in the ceiling and conduit and other places that can affect communication. So therefore, cabling in those spaces have to be also considered to look for where do we have emitted radiations. And as you identify those different areas where certain power systems are being run, you will then start elevating the hazard environment for these elements. So you would anticipate to find some presence of dust and water, some presence of chemicals, as you start coming down to the systems where you have machines, where you have some drives, cabinets, where you have some tanks and so forth. And even within those environments, you will see there are certain areas where you have more extreme conditions. So you see the severity of what type of cabling we need to deploy at any one of these points depends on what is the hazard that's present in that layout. So in the red areas, those are areas where you need to apply the maximum amount of severity type cabling. So you would choose the right cable that can withstand an M3, I3, C3, and E3, and you will pick up the right connection that can take those same extreme environments. Now, what happens if you use anything that does not conform to these specs? If, for instance, you choose to use a commercial grade cabling and connectivity in an M3, I3, C3, and E3, you would most likely be able to run the system. You will have some intermittent connectivity issues because of electromagnetics that will affect your cable because it's probably not shielded. You will also encounter a lifetime situation. A cable that's rated to be used in an office space for 25, 30 years will end up maybe lasting you 1 or 2 months, especially if there are chemicals attacking those cables. So these are real hazards you need to worry about. So then we see, okay, what do we need to do when we are trying to lay out our networks? And when do we use what type of a support system for our devices? So this table, for instance, shows you that if you are in an office space, you could actually use hangers to put your cables, to run your cables, or even trays. So as the severity it changed from clean environment, an office space, to very dirty, you will see that we need to apply some type of norms to running cables through different type of a conduit and different type of support systems so our cables are protected. So how do we protect our cables? If you put your cable inside of a conduit system, then you're basically changing what you call a commercial grade type cable. If you put it inside of a conduit, you give it a additional protection so it can take more dirtier environment because the conduit is protecting it. You have to worry about condensations, and that could be an issue. So therefore, when you start running cables inside of a factory, you need to be made aware what are the hazards and what type of route type I need to apply to run my cables in. And that is how we go about doing this. Now, similarly, you need to be informed that when you take commercial grade products, commercial grade products are generally cheaper than industrial grade products. Why? Because they're made with less protection. So cable, for instance, doesn't have to have shielding. That's an extra protection that doesn't cost as much to do. As you move from an office area to a machine level inside of a factory, then the cost for cabling and connectors change. Okay, what does it all mean? We try to apply the M.I.C.E guideline everywhere possible in an industrial space to give us the best protection for our cables and connectors. And we have to be cognizant of these costs. So if, for instance, certain solution is very expensive to apply in a certain area, we will try to find out, are there mitigations that we need to apply to protect that device at the edge point. So we could potentially be using commercial grade product inside of a factory if we have the right protection to each and every one of those systems. Enclosures, for instance, can be those types of protections. So inside of an enclosure, you could put commercial grade product as long as the enclosure is made out of stainless steel and it's got the right gasketing so water and dust cannot get into these systems. So these are the things we will always apply, which is common sense when we're running these systems. Now let's start looking at the architecture again and what it means. On the left-hand side, you will see a star topology that we talked about earlier. And this star topology basically says that at the edge devices, this is where we have the extreme condition that we will encounter inside of a factory. As we go up, and you've seen it in the other slides, the color changes from red to yellow, and yellow means that it's lower M.I.C.E category. So at the DC level, this is where you have what we call distribution C type enclosures, where we find data centers and everything else. This is the environment where you could use commercial grade product for all of it, including the enclosures. As you come down to the next layer in the star topology, where now you are on the factory floor systems, you're talking about distribution Bs and so forth. Those type of distribution frames and zone enclosures are the type of systems that inside each one of those enclosures you may encounter commercial grade product, but connectivity on the outside and between these devices have to follow the M.I.C.E norms. And as you start looking at each one of these points, you will find that at distribution A, this is where connectivity is probably at a M.I.C.E 3 category, and you have to worry about that environment. When you go to a B, you will encounter more of a M.I.C.E 2, and you go up to C and you find a M.I.C.E 1 category, where you really shouldn't worry about that environment. Connectivity between these points also is something to worry about. So generally in a star topology, communicating from a control room to a distribution frame outside in the network, outside the factory systems, the distance between that micro data center and a distribution point on the floor can be a long distance. Generally, cabling between those two devices are fiber. So fiber connectors and fiber cabling that runs between these devices have to be capable of withstanding M.I.C.E 1 or M.I.C.E 2 type environments. And as you go down in the architecture, there may be a need from between distribution frames and zone controllers and zone enclosures where the M.I.C.E category might be at a higher level. And you need to make sure that your cabling can withstand those environments. And the run there can be fiber as well. Now, what we call the last mile in a network is where a zone controller is connected to the edge devices. All the cabling that's run between those systems are generally copper. So why do we run copper at the edge devices versus fiber? Copper connectivity is sturdier, and there is a lot of connectivity solutions that you find selling in the industry that are copper connections. You will not find many companies delivering fiber connectivity to the edge devices. Generally, the connection between an edge device and a zone enclosure is in under 100 meters. Therefore, you could use copper. The specification 568 and 1005 state that when you run copper cabling, you need to follow the guidelines that you shall not exceed a length of 100 meters. Running fiber, you could go at a higher distances. So shorter distances are generally copper, and this is an extreme condition. Now we're talking about edge connectivity, where you have a 3 category for all of the M.I.C.E elements, to a fiber that is now connecting above the subsystem 1. So anything from cabling subsystem 2 and 3 can now be running fiber between those devices. You could also run copper if these distances are not, like I said, 100 meters. So in a small factory, you might decide to run copper throughout. But generally, we are on fiber between these enclosures. So now brings us to what we call a logical architecture. When you look at a network, as you see in this picture, basically says that I need to have a connection between an edge device and an LWAP. It's a WAP device. That type of a connection, the way it's showing right here, it's a certain dedicated connection. It does not tell me how long that connection is. It's basically saying when you look at an architecture, you have a need to connect point A to point B. It does not tell me how long. It does not tell me what type of wiring is required. All it's saying, it's logically how these connected systems are running together. So when you look at level 1 in this architecture, you find different cell areas. Each one of those cell areas are independent and they run totally autonomous, but the data that's shared from cell area 1 to cell area 2 has to be shared across very dedicated lines. In this architecture, you'll see that there is a point where we have distribution switch, where it's collecting all the input coming in from zone cell area 1, 2, and 3. That switch now is basically collecting all the data coming in from these different cells, and it's communicating to the second and third layer in the architecture. This architecture, this logical architecture, is another representation of what TIA 568-1005A shows you in the star topology. There is another name for it that we use in the industry, which we call CPWE, and it's basically called Converged Plant-Wide Ethernet. The terminology of Converged Plant-Wide Ethernet is a terminology that's used by Rockwell Automation, by Cisco, and by Panduit. And it's basically laid out on what we call the network Purdue model in communications. So you see at the cell level, you've got a lot of devices at what we call edge connectivity. In the middle, you've got HMI SCADA systems. As you go up in the architecture, you encounter what we call a DMZ space, and this is the demilitarized zone. This is where we find firewalls and so forth to separate the networks from a industrial network and an enterprise network. And why do we use firewall? We use firewalls to protect the factory systems from attacks outside the firewalls. Also, we tend to manage traffic between the enterprise world and the factory world. They're two different worlds. On the factory system, the communication is real time. It's happening in nano and micro second speed. When you go up to the enterprise, communication does not happen as fast and as frequent as it is on the factory side. So you separate those networks by a layer that we call demilitarized zone. As you go up in the star architecture, you reach the central point here, which we call the data center space, the enterprise space. At that space, you find a lot of commercial communications, not so much factory, but commercial. And a lot of the data, or some of the data, reaches from the edge device to the enterprise, but not all of it. So how do we apply that same architecture when we are deploying different solutions in a network? At the enterprise level, this is where you find a lot of data centers. In a factory system, you will find what we call a micro data center, similar to what you find in enterprise, but they're generally one or two closets or switches and distribution frames and network communication hubs and so forth. As you go down in the architecture to the factory systems, this is where you find more of what we call distribution frames. In a distribution frame is similar. The hardware inside these enclosures are similar to what you see on the enterprise side. So you find commercial switches and gear and commercial type connectivity and fiber inside these enclosures. The outside of these enclosures are usually hardened to withstand the environment condition. And as you go down in this architecture, you reach the real world. And a zone network system, for instance, is a place where you encounter a lot of limitation on what type of connectivity you need to have. Not so much inside these zone network systems, but on the edges where you connect from that enclosure to the edge device. So there are devices and connection point that needs to be architected and designed into the network to withstand these environments. So now you saw in the architecture, we have different method of deploying the network. On the left-hand side, you see that this is what we call the star topology. In this type of a network, you see that there is a one point where all of the factory systems are connected on a single wire. This is a very quick way of connecting a certain network, but in fact, it's not the most efficient way. Why is that? If at any point you need to be aware that in some areas, like you see on the right-hand side, area 3 in this architecture is what we call a M.I.C.E area. So suppose that the group of systems in the 3 area are requiring a level 3 cabling and connectivity. That means that you would need to run 6 cables from area 3 back to the center in a star architecture, as you see on the left-hand side. So, and this type of cable will have to be a 3 rated cable. So you have 1, 2, 3, 4, 5, 6 rated level 3 cables in all of its M.I.C.E rating that have to be run the length to get it to the central system. That is a very inefficient way of running a cable because that is an expensive cable to start with. And then secondly, it's going to be running for a good long distance. You will, in this type of what we call a zone architecture, deploy a one cable to all of the different zone enclosures that are laid out at different places in the factory, and then use a level 3 cabling within an area. So the runs would be shorter. They don't have to be as expensive run as the other case back here. And within a certain area, there could be one space that's at level 2 and one space at level 1, or one space at an office space. So you have to then worry about what will be the cost to run this, for instance, this signal cable, and that's a similar cable back here, back to its central point. So architecting a network and basically separating the zones into different zones and so forth will mean that from a central location to each one of those zone controllers, you are running fiber, and that depends on the distance, of course. And it's also running at a ceiling level. So therefore, you would need maybe a zone 1 or a level 1 M.I.C.E for this green cabling going to different zones because they happen to be running in a ceiling environment. And inside the cell, you will then have to worry about the M.I.C.E rating. That makes it very efficient way of distributing the network. If a certain cable is broken inside of a cell, you're affecting just the one area in the cell. You will not be shutting down all of these different areas to run a cable from the central system to the affected zone. So these are ways of running a network inside of a factory where you have to really consider the zone, the M.I.C.E rating, where you have to really consider the architecture, where you try to optimize the cost of your cabling and connectivity. So let's look at the benefits, why M.I.C.E is important to what we do. We know that when a certain company chooses a M.I.C.E rating that's at a level 3, that means the device has been tested to withstand those environments. So you will trust that these cables at 3 level rating for M, I, C, and E are going to be good cables for what you need. The connectivity also would be tested. So it is important to choose those M.I.C.E rating when you're deciding an architecture. And one thing to consider, you could use commercial grade product in a factory system if you know the right of environment that's going to be run into. So you don't always need a level 3 for running systems. So now we'll talk about what kind of capabilities we have coming from Panduit. And you'll see here that the TIA system 2 and 3, sometimes we use a level 1 product. And why do we do it? Because it's running inside enclosures. So in a level 1 type product, you would expect to have certain no environmental rating issues, office grade. You will have higher bandwidth. You would need solid copper cabling and fiber in some instances to run these networks. And you don't have to worry about the shielding. You don't have to worry about twisted pairs. You don't have to worry about the long distances and the hardness on the cable. A lot of these plastic type RJ45 connections, which you see in the office, would work just fine in a factory environment at these ratings. So therefore, you don't go over specify some areas. When you start looking at higher rating product, now you have to start finding the right protection. And where do you find this? You find it at the edge devices. So you see this is a style of an RJ45 end connection, and it's got its own what we call a environmental boot. So it's closed, it's tight. You will find these types of connectors that we call the M12 style connections, where you plug in and then you lock down the jacket on its connection with a screw type connection. A lot of these devices, every single one of these devices could run Ethernet cabling at this point, but the type of wiring has to be a certain way. A 6A is what generally used. Shielded product are required at these points. What type of a D and an X connection, depending on the speed of the network that you're running. Does it have 2 pair? Does it have 4 pair? What type of jacketing we need to use? So at some point in this presentation, you will see that different style jacket, for instance, are used at different points. So choosing if you need to use a PVC or a TPE or a PUR type jackets for a certain cable is important when you're running these cables through chemical and so forth. So you look at PVC and you say, okay, it is good rated, it has some abrasion resistance and so forth. But as you start looking at different rated product like TPE and PUR, you will find where you have extreme conditions where TPE or a PUR jacket will be preferable. When you have high flexing, you have to have different patch cords that can be rated for high voltages around them, that is. All these cables are designed to handle 24 volt, but with the right shielding on the cable, it can be run next to a 600 volt line of power. So that brings me to this table. In this table, oops, we're seeing an issue with PowerPoint here. Uh-oh. Excuse me, folks. I don't know what happened just now, but I'm seeing an issue with my. For some reason, the PowerPoint stopped. Yep, it's. I'm running through it back to this table right here.
Okay.
So in this table, you will see when we need to use copper or fiber, what type of shielded or unshielded type of connectors and cables we need to use, and what it means in terms of cost, in terms of protection, and so forth. So This table is kind of a quick way of deciding, should I use the cost cost conscious type of unshielded twisted pair versus a shield twisted pair. So that makes the difference between UTP and STP. And when do we use it? 5E versus 6 type 6 cabling is used in certain areas. So category 6, for instance, is used for higher signal and noise. This is where the standards are moving toward higher categories. When you use copper versus fiber, the distances being one of those concerns, and you could see here that anything less than 100 is copper, anything over is fiber. The MI protection is higher for fiber. Why? Because fiber is not affected by power systems. So light and power, I mean, that's not a concern there. When you look at the fiber, having a single mode versus multi-mode also is determined by how far you could run these cables. So multi-mode fiber, for instance, could take you up to 2 kilometers. When you go single mode, and that's a very expensive type of a cable, you could go to 40 kilometers. So again, the determination of when to use shielded versus unshielded, copper versus fiber, a 5E versus 6 versus 6A, all of these different specs have to be taken into consideration. And that brings me to this slide. Panduit created what we call a M.I.C.E guide for all of our devices on the industrial side. In this M.I.C.E guide, you could basically select any one of the components that we have in our industrial offering and determine very quickly by looking at this shorthand cable if that device, that copper cable, for instance, can withstand a mechanical 2. It does not, we don't care about ingress, that's not an effect in this area, so it's not signaled. And it can withstand a chemical environment at a level 2 and an electromagnetic at a level 2. That is a quick way to determine Panduit components and the environment that they will survive in. If you ignore this and you say, okay, I want to determine what type of cable I need, then you start looking in the mechanical spaces and you'll see that you have to worry about shock to certain rated level and how many newtons does it take and so forth. For a lot of these high technical level limits, Panduit has taken the time to do all of this testing and decide that the mechanical environment that could survive all of these environments at a level 2 is being considered. So we consider shock vibes, tensile stress, compression, and so forth, and they all passed at level 2, and it's good to go. So you see, this is a guide that you could find on our website. You could download, you could do whatever you want. It's available in different media. And you could basically look quickly at a certain device and decide how can I use it and where. Now, we have had different implementation, and you could find a lot of different use cases on the Panduit site. This is a specific use case that I'm sharing with you today. It's with Noosa Yogurt. Noosa Yogurt is a company in the Midwest that decided to build a completely out of the ground a greenfield, what we call a network system. And in doing so, they decided the right way. They architected the network the way we described here in a star type topology, decided what M.I.C.E rating, cabling, and connectivity need to be run between all of it. There was several partners working on this type of a solution. The system was architected, it was built with the right types of enclosures, and you see some pictures here, so you could go read about it and see there is even a video that you could look at what type of solution and how how it made sense for NUSA to implement, for instance, stainless steel type enclosures and so forth. The, the point I'm trying to make is this. Every one of these implementations, Panduit worked through partners. So we call what we call ecosystem partners. They're distributors and design partners and installation partners that work with certain guidelines for what type of Panduit components need to be used and how and when and so forth. And they will deploy these networks. In this case, we've got Melisco Engineering for a system integrator and Piper Electric for installer. The distribution participated in this by delivering the component to these end users. NUSA is a good use case. You could also go look at other use cases on the network as well. There are also different resources where you could get at this information. And there are links here. So when you do get copies of this presentation, you could click on every one of these links and be able to reach at the electronic versions of the M.I.C.E guide or look at different things that we offer. All of this material is all available electronically, and you could have access to it. With this, I'm ready to take your questions. So, Jane,
Thanks,
do we have
Michael.
any questions?
Let me take a look here. We will use this time for any questions. It looks like we have a few minutes left. If you want to utilize the chat box on the GoToWebinar app, you can put your questions right in there. Michael, and you're right. It looks like we did have a couple here, so I'm going to go ahead with the first one. The question is, you mentioned that we do not always use industrial-grade cables and connectors in a given project. Can you go over this point with more detail?
Sure. So, we said that the M.I.C.E basically tells us that we need to protect our connectors and cables when we're running them in factory systems. When we determine the M.I.C.E level in a given area, the choice can be to use a level 1 graded products. Generally, as a rule of thumb, we find that when we look at the entire manufacturing space, we find that 60% of the material deployed in a factory system can be commercial grade products. And the remaining 40% will have to be industrial. Where do we use industrial? We use it generally at the edge devices, at the edge points. We use it inside of a work cell where you have a lot of moving parts, a lot of the cleaning requirement, daily wash down requirements, and so forth. This is where you need to have the best protection of your network, where you are encountering the chemical, the solvents, the dust, the movement, and so forth. Anything above these areas in the ceiling, in between distribution frames, from the factory to the edge, which would be the other edge, the micro data centers, all of these networks can be commercial grade products. So when you're deciding where to use what, you always have to balance your cost and your protection. Always consider to run the cable that can withstand the extreme conditions of its run. So if a cable is going to be run over chemical tanks, that cable has to be at a rating level that the chemical tanks will allow you to run. So it could be at a 1, but if these chemicals are very harsh, then you need to make sure you use a level 3. I hope that helps.
Yeah, that was great. We actually, I think, have time for one more question. The second question is, where can I get more information on the benefits of Ethernet in industrial communication?
Okay, there is a consortium that's called IIP Advantage. This is and I don't believe I showed it today, but it is a place where it has an internet link and so forth. So please reach out to us so we could send you those links. And basically, this is a website, IIP Advantage, it's called, where anyone could go in and look at how to, what are the advantages of running Ethernet, how to run cabling, and so forth. This is a training website that's available to a lot of users, and there may be some cost to look at these things, but if you reach out to Panduit, we have ways of getting you access to these web pages so you could reach the data and learn more about it. That would be one place. You could also come back to our partner hub, and we call it, it's partners.panduit.com. This is a place too where a lot of different system integrator and installer partners come in to learn more about Panduit solution, Ethernet communication. A lot of classes are offered on that website. So I welcome you to go check it out and let us know if you need our help in doing any of it.
Okay, thank you so much, Michael. I think we are at the end of our hour now. I wanted to thank everybody for the questions and your time today. This will conclude today's webinar.